In this video, we're continuing section 3.5 on inverses, and we are going to focus on how we can find and sketch the graphs of inverse functions. All right, so let's get into an example where we're trying to find the inverse of my function and sketch both f of x and f inverse of x. All right, so in part A, our function is x minus 1 cubed plus 8. Okay, so to do this, first, let's just rewrite f of x as y. So we'll get y equals x minus 1 cubed plus 8. Okay, so the first step of finding an inverse function is we switch the x and the y. We switch the x and the y. So instead of writing y, I'll write x. And on the other side, I'll have y written instead of the x. So y minus 1 cubed plus 8. So you swap them. And then step 2 is, well, now that they're swapped, try to solve for the y. Try to isolate the y. Okay, so maybe first we can move the 8 over to the other side. So that'll give us x minus 8 equals y minus 1 cubed. And now we can cube root both sides to get rid of this third power. So that'll give us x minus 8. That is getting cube rooted. On the other side, if I cube root, it'll cancel out that 3. And we'll just have y minus 1. I don't need to plus or minus because I took an odd root of both sides, not an even root. And now I'll add the 1 over to the other side. And maybe let's rewrite it so that the y comes first. So y equals cube root of x minus 8. And then we add that 1. Okay, so once that y is isolated, this is the formula for the inverse function. So we get f inverse of x equals the cube root of x minus 8 plus 1. All right, that's my inverse function. So now let's sketch the graph of the original function, and then we'll also sketch the graph of the inverse to see how they compare. All right, so with the original function, I want to start with the parent function. So the parent function for this graph is going to be y equals x cubed. Let's start with that. So let me draw an axis. Let me draw a coordinate plane here. Let me draw a couple of sets of axes just to get ready for each step where I will shift it or reflect it. Okay, so I got y equals x cubed. And the next step, now I'm gonna, I'm working inside out, I will deal with that x minus 1. So I'm gonna replace that x with an x minus 1, replace the x with an x minus 1, and doing that, that shifts the graph right by 1. And whoops, sorry, I realized I forgot to even draw the graph of y equals x cubed. Let's go back and do that. So y equals x cubed, that's the graph that kind of snakes upwards like this. It gets momentarily flat at the origin, and then it keeps on going up. Okay, and once I shifted it right, well, this inflection point at the origin, that moves 1 unit over to 1 comma 0. And it curves like this over here, and then curves in the opposite direction on the other side. Cool. All right, and now I got to put in that plus 8. So we get y equals, whoops, sorry, let's switch it to black. Y equals quantity x minus 1 cubed. And then we'll have that plus 8 at the end. Plus 8 at the end. And that shifts the graph up by 8. Okay, so I'm going to start with my inflection point and move that up 8 units. So that'll put that at quite high. That'll put it at 1 comma 8. 1 comma 8, and it's curving downwards here. This side is curving upwards. All right, so we got our graph. So that is my graph of the original function. That is the graph of the original function. Okay, so the problem also asked me to sketch my inverse function graph. So the inverse formula was here, so let's sketch that function. Let us sketch that function. Let me zoom it out a little bit so I can see this. Okay, so again, I'm going to start with my parent function for this formula. So for that formula, I think the parent function is going to be the cube root of x. The cube root of x. Let me draw some axes. And we actually haven't drawn this one before, but the cube root of x is a little bit like the square root of x graph in that it has this point of the origin, and then it curves upwards like this. But unlike the square root of x graph, like with the square root of x graph, we're only allowed to plug in numbers inside that are greater than or equal to 0. But if I have an odd root, I can totally plug in negative values for the x. So we're also going to have a part of the graph with the negative x values. And it turns out that that looks like this. It kind of mirrors the part in the first quadrant. Okay, if I wasn't sure about how I got this, I could totally plug in some values for x. Like I could plug in x equals 1, and x equals 0, and x equals -1 to see what I'm getting out. But it turns out when we do that, we'll get this sort of shape. Okay. All right, so now let's start to shift this and reflect this to get our inverse function graph. So let me draw a couple more axes. A couple more axes here. All right, so looking at my inverse function formula, again, working inside out, I'm probably going to want to replace the x with that x minus 8 next. So y equals cube root. Replace that x with an x minus 8 inside the function. So that is a shift right. That shifts the graph right by 8. Okay, so when I do that, this point, that inflection point gets shifted 8 units to the right. 8 units to the right, so that is now at 8, 0. So over here, it is curving upwards like this. In the other direction, it's curving downwards like that. Okay. All right, one more thing to put in, which is that plus 1. So I'll get y equals cube root of x minus 8. Now I'm going to put in that plus 1. So that plus 1 at the end, well, that's going to shift the whole graph up by 1. So that shifts it up 1 unit. So this inflection point moves up 1 unit. So now that's going to be at 8, 1. Curves like this, going that way, and then going down, it curves like this. All right, that is my inverse function. That is the graph of the inverse function. Okay, so there's one key observation that I want to notice about the graphs of the original and the inverse function. So the inverse function graph takes all the points on the original, like 1, 8, and it switches the input and the output. Like notice 1, 8 became 8, 1 in the inverse graph. That's happening to every single point. Every single point switches the roles of the x and the y value. Graphically, what that's going to do is, if I were to draw the line y equals x, through the origin, it's got a slope of 1. What happens is the inverse graph is the reflection of this original graph across that diagonal line y equals x. So f and f inverse are reflections. They are reflections across that diagonal line y equals x. Okay, that is the key graphical fact about how the original and the inverse are related. Okay, so another thing I want to observe about the function and its inverse is that when I look at the domain of a function, recall the domain is referring to all the inputs. Well, what would that tell me about the inverse function? Well, with the inverse, so the inputs of the original should be the outputs. They should be the outputs of the inverse. But the outputs, well, we call that the range. So in other words, the domain of f equals the range of the inverse. Similarly, if I look at the domain of the inverse, domain being the inputs, well, the inputs of the inverse should be the outputs of f, and the outputs, well, we call that the range. So when you go from a function to its inverse, it'll switch the role of the domain and the range. Okay, in other words, the domain of f equals the range of f inverse. So like in the example I just did up above, if I look at the domain of f of my original, well, that should be equal to the range of the inverse. And, from the graphs, like if I look at the original graph, what's the domain of it? Well, every x value is in the domain. It's negative infinity to positive infinity. But I could also see that if I look at the graph of the inverse and find its range. If I think about what y values we get from the inverse graph, well, it's also everything. Okay. All right, all right. All right, let's flip it to the next page and let's look at another example here. Let us look at another example. All right, so now I want to do the same thing, but for the graph of square root of x plus 1. All right, so first, let's get the inverse. Let us get the inverse. All right, so I'm going to rewrite f of x as y. Y equals root x plus 1. And then first we switch the x and the y. Switch the x and the y. And in doing that, we get x equals root y plus 1. And now I want to try to solve for the y. So I move the 1 over, I get x minus 1 equals root y. Then I can square both sides, so we get x minus 1 squared equals y. Okay, awesome. So I got the y isolated. So we got the y isolated. Okay, so the problem asked me to think about, what's the original graph going to look like? What's also the inverse graph going to look like? So at this point, let me draw some axes. Let's draw some axes. So I'll come back to thinking about the graph of the original function, but for right now, let me just focus on the inverse. So y equals x minus 1 squared. So y equals x minus 1 squared. This is in vertex form. I can see the x coordinate of the vertex is 1. And the y coordinate, well, if I do plug in 1 for the x, I get y equals 0. So it's going through the point 1 comma 0. That's the vertex. And it's an upward facing parabola because the leading coefficient is positive. Upward facing parabola. So something like this. Something like this. Okay. But there's a problem with this being the graph of the inverse. Because an inverse is supposed to pass the horizontal line test. This fails the horizontal line test. So what does that mean then? Like, should that have happened? Like, let's look back to my original function. If I think about the original function, I'm first going to graph the parent function, which is y equals square root of x. So let me draw some axes. Axes. And the graph of y equals square root of x starts at the origin, and then it curves upwards like this. So now let's add in that 1 at the end. Y equals square root of x plus 1. Again, I'll draw my axes. And if I add the 1, well, that's going to shift the whole graph up. The whole graph is going to go up by 1. All right, so that initial point now is 1 unit higher. It's at 0, 1, and then I still got that same general shape. Okay, so that's part of what the problem wanted. It wanted the graph of the original function, so let me just box that. But if I look at the original function, this definitely passes the horizontal line test. So it should have an inverse. But with the inverse formula I got, it didn't pass the horizontal line test. It failed the horizontal line test. So what I then need to do is, so if this happens, if we know a function has an inverse because it passes the horizontal line test, because that's what was happening here. But when I find the inverse, like I did, if that inverse isn't passing the horizontal line test, that's probably an indicator that we need to restrict the domain, or like we're somehow not considering the domain. So like maybe I'm not supposed to look at the whole parabola I just got. Maybe it's just be part of it. So how do I know what to restrict the domain to? Well, I gotta look at my original function and find the domain and the range of the original. So in my original, let's find the domain, let's find the range. So my domain, my x value start at 0, bracket at 0 because I do attain a point when x is 0, and then they go onwards to infinity. The smallest y value is 1, bracket at 1 because I do attain that y value 1, and then they get bigger and bigger and bigger, so onwards to infinity. Okay. All right, so here's my domain. Here is my range. So with the inverse function, the domain and the range are supposed to get swapped. So for the inverse, for my inverse now, let me write it here. My domain and range for the inverse should be the swap of these. So what this range was, that's what the domain of the inverse should be. This should be 1 to infinity. And then the domain of the original should be the range of the inverse. So 0 to infinity. Let me highlight those. So those are the same, and those are the same. So now, when I go to write my inverse function, so the inverse function has this formula x minus 1 squared, but now I know what the domain should be restricted to. It's just, my domain is just x values that are greater than or equal to 1. So if I draw my axes, I'm only going to be drawing the part of this parabola where x is greater than or equal to 1. Okay, so that's just this half of the parabola. It's just the right half of the parabola. Okay, so here's my inverse function formula. That's part of what it wanted. It also wanted the graph of my inverse, which was this. And now I have it. Okay. So this was definitely a more complicated example. But again, the key takeaway is, if I find the graph of my inverse, but it doesn't pass the horizontal line test, like I ran into here, that probably means I need to go to my original function, find its domain and range, and then those are going to get flipped to get the domain and the range of the inverse function. And then once I know the domain of my inverse function, that'll tell me how I should limit my graph. And when I do limit the graph, notice, well, now it does pass the horizontal line test, so we're good. Okay. All right, let's take a look at, a different flavor of example here. All right, so for the next one, I'm going to assume my function has an inverse, and let's let f of x be square root of 3x, and then plus 10 on the outside. It says to find f inverse of 12 without explicitly computing the inverse function graph. So without actually, finding the inverse function formula first, can I find what f inverse of 12 is? Okay, so let's think about this. I actually want to first have you try this question on your own. I want to have you pause the question for about a minute and see if you can think about how you might begin this question. It's probably not going to be enough time to finish it in a minute, but think about how you might get it started. Pause it in 4, 3, 2, 1. Pause it, and try this for about a minute. All right, so hopefully you paused it and tried it for about a minute. Let's talk about it. Okay, so we are looking for we're looking for f inverse of 12. So I don't know what that is. Let me start off by saying, let's let that be equal to something. Maybe I'll call it a. So what I'm going to do now is I'm going to rewrite this in terms of the original function. Because I don't know anything about the inverse, but I do know something about the original function. So the original function should switch the role of the input and the output. So a is now going to be the input. 12 is now going to be the output. Okay, well, what is f of a? That means I got to take the a and plug it into my formula where the x is. So I'll get square root of 3a plus 10 outside equals 12. Okay, now I just rearrange this. Subtract 10, and I get root 3a equals 2. Square both sides, and I get 3a equals 4. Divide the 3, and I get a equals 4/3. Okay, so we got a. Technically, I solved an equation that had a square root, so I should check for extraneous solutions. Let's do our check. Let us do our check. So if I plug it back in, I get square root of 3 times 4/3. And then outside, I got that plus 10. And I want to know, does this equal 12 when I do this? Well, inside my square root, these 3's will cancel. And I'll get square root of 4, which is 2, plus 10. And yeah, that does equal 12, definitely. So I'll put a check mark there. Awesome. So this answer does work, and I got it. I got my value of a. Okay. So the takeaway from this is, if a problem asks me to find f inverse of a number, I can even do that without first finding a formula for the inverse function by keeping in mind, well, the input of the inverse function is the output of the original. In other words, I sort of just made this number 12, be the y value. And I tried to find, well, what x value would I have to plug in to get this out as the y value? Okay, all right, so let's end this video with one final example. So this is going to be like the previous problem. I want to find the inverse of this function and then sketch both the original function and the inverse function graph. So this one, I want to give you some time to try. Pause the video for 4 minutes this time. And try this on your own first. Pause it in 4, 3, 2, 1. Pause it, and try this one on your own. All right, so hopefully you did that. Let us talk about it. Okay, so first, I could think of f of x as being y. Let's switch the x and the y. So switch, let me write that better. Let's switch the x and the y. So if I do that, I will get x equals negative root y and then plus 1. And then I got to isolate y. So maybe I'll move the root to the other side so it becomes positive. And maybe I'll move x to this side. Okay, so that'll give me, negative x and then plus 1. All right. And now I can square both sides. Let's see, if I square both sides on the left, I'll get y. On the other side, I'll get negative x plus 1. And that, negative x plus 1, and that whole thing is getting squared. So negative x plus 1, and that whole thing is getting squared. Okay, so well, I notice I have a quadratic here, so its graph is going to be a parabola. Okay, so let's draw that parabola. Okay, and it's kind of in vertex form for us. What x coordinate would I plug in here to make this part be 0? Well, I would plug in x equals 1. I'd plug in x equals 1. And if I do plug in x equals 1, well, the y value happens to then be 0. Okay, so my parabola's got this vertex at 1, 0. If I were to FOIL this whole thing out, it turns out if you do that, you get x squared minus 2x plus 1. But that leading coefficient is positive, which means it's an upward-facing parabola. It's an upward-facing parabola. Okay, so that is my graph. That is my graph of y equals parentheses negative x plus 1 getting squared. Okay. But this, unfortunately, fails the horizontal line test. It fails the horizontal line test, but an inverse is supposed to pass the horizontal line test. This is very similar to the example that we did above. So, maybe it's a matter of, maybe the domain isn't supposed to be the whole thing. Maybe it's just going to be part of the parabola. So how do I figure out what part? Well, I have to look at the graph of the original and first find the domain and the range of the original. Okay, so let's think about the original. So we already graphed square root of x above. Let me not draw that again. Let's start with the graph of negative root x. So putting a negative in front of my function will reflect it across the x-axis. So that'll flip my square root graph downwards like this. And then if I add 1 at the end of the formula, that's going to shift the whole thing up. If I add that 1 to the formula, it shifts the whole thing up. So now this y-intercept is at 0, 1. And then it is curving like this. Okay, so that's the graph of my original function. Let's write down its domain and its range. So domain, my x values start at 0, bracket, that is included, and then they get bigger and bigger and bigger, onwards to infinity. My range, the smallest y value, well, the y values get smaller and smaller and smaller and smaller and smaller forever. So they are starting at negative infinity, parentheses, and then they get bigger and bigger and bigger and bigger until they reach 1, and bracket at 1, because I do reach that point where 1 is. Okay, so I got that domain, got that range. Okay, so there's my range, there's my domain. So when I go to my inverse function, when I go to the inverse, the domain and the range should get swapped. So the domain should be negative infinity to 1, and the range should be 0 to infinity. So let me highlight these so that they match with the corresponding domain and range in the original. Okay, so now I am ready to write down my inverse function. My inverse function Well, it's going to have this formula, parentheses negative x plus 1 squared. But now I know what the domain is supposed to be, like how to limit the x values. Based on this domain, well, it's saying that, well, x is actually less than or equal to 1. All right, so let's draw that. Let me draw my axes. If x is less than or equal to 1, well, that is just the left half of my parabola. That is just the left half. So from that vertex point and just the left half of it. Okay, and now this graph does pass the horizontal line test like I needed to. An inverse should pass the horizontal line test. Okay, all right, so I'm going to box my inverse formula, box that graph. It'll also ask me to sketch the original function, so I'm going to box that as well. Okay, but again, I really want to emphasize the key takeaway. If I'm finding an inverse function, once you find it, always do a quick check to see, well, does that, I'm going to pass the horizontal line test. So if it's a quadratic like this, it won't pass the horizontal line test. And that often means, maybe I got to limit the domain. And the way I figure out how to limit the domain is drawing the original first, find the domain in the range of the original, and then those should get flipped to get the domain in the range of my inverse function.